Hi, good morning. I welcomes you for the today's session about dielectric materials. What is that? Dielectric materials. This is today's session. Let's see what are the topics are covering in this session. Dielectric materials interaction, types of dielectrics, difference between polar and non-polar dielectrics. Classification of dielectric materials, dielectrics characteristics, various polarizations, internal field, classes, Moshe's relation, properties of good dielectric material, applications of dielectric materials, classical theory of electronic polarizability. So these are the topics we are going to cover in this session. Let's see what is interaction. In interaction, a dielectric material is defined as the non-metallic material with specific resistance high, temperature coefficient of resistance negative, and large insulation resistance. So the specific characteristics of dielectric material is what? That is specific resistance high, temperature coefficient of resistance is negative, insulation resistance is large. So these are the specific resistance specific characteristics of dielectric material. What are that? Specific resistance high, temperature coefficients of resistance negative, large insulation resistance. In other way, how it can be defined? In other way, it will be defined as dielectric material is that it is non-conducting material which stores electrical charges electrical charges which stores electrical charges. So here, in other way, how it is defined, dielectric material is that it is non-conducting material which stores electrical charges. The term dielectric was first introduced by William Wavell. Who introduced? The term was introduced by William Wavell. So here the term is a combination of two words. Which term? Dielectric is a combination of two words and it is defined as dia and electric. Dielectric is a combination of two words of dia and electric. The electrical conductivity of a perfect dielectric is zero. What is that? The electrical conductivity of a perfect dielectric is zero. A dielectric stores and dissipates the electrical energy similar to ideal capacitor. How the ideal capacitor works, how the ideal capacitor dissipates the energy, and a similar way dielectric stores and dissipates the energy. Conductor material starts conducting when electricity is applied. We know that conductor material starts conducting when electricity is applied. An insulator opposes the flow of electricity as it does not have any free moving electrons in its structure. So here, what is the use of the conductor? What is conductor? Conductor is conducting electricity when applied. And what are the examples of the conductors? That is, rub, sorry, all the metals are the examples of the good conductors. Coming to insulators, that is the example is what? Rubber, wood, plastic. So here, what is an insulator? An insulator opposes the flow of electricity as it does not have any free moving charge. So there are no free moving charges, free moving electrons in insulator. That is the reason flow of electricity is not possible. But in dielectric, it's a special type of dielectric is a special type of insulator not conduct electricity. It is also a special type of insulator which not conduct electricity. But what is happening when electricity is applied? Sorry, when it is applied to the electric field, it will be polarized. It gets polarized subject to the electricity. It gets polarized subject to the electricity. Let's see what is polarization. That means dielectric polarization is what? When a dielectric is placed in an electric field, the electric charges do not flow through the material. Do not through the material. Instead of flowing through the material, what they are doing? Let's see. Electric charges slightly shift from their average equilibrium position. The positive charges present in the material gets displaced in the direction of the applied electric field. The negative charges are shifted in the direction opposite to the applied electric field. This leads to dielectric polarization. What is that here? Just electric field. Imagine a electric field. In this electric field, just imagine this is as of so this is the dielectric material. This is the equilibrium position of the dielectric. So around this equilibrium, positive and negative charges will be presented. So when once it is placing the electric field in whatever direction the electric field is applied, in the same direction from this equilibrium position of the dielectric, the positive charges are moving. The positive charges are moving in the opposite direction to this applied field. Opposite direction to the applied this electric field, the negative charges are moving from the equilibrium position. So from this equilibrium position, in the same direction the positive charges will be moving, and in the opposite direction from the equilibrium position, the negative charges are moves to the applied of electric field, opposite to the applied so positive charges moves in the same direction, negative charges moves in opposite direction to the applied electric field. So here what is happening? The positive charge and negative charge both will be separated. The positive and negative charge both will be separated, and this leads to form dielectric polarization in a dielectric material. So here the separation of positive charge from the negative charge with the help of electric field is defined as dielectric polarization. Let's see here we have the schematic diagram. Here this is an electric field. Here in the electric field, in the same direction the positive charges are moving, and the opposite direction the negative charges are moving. Because of this reason, moving of the positive and negative, there is a space between the two charges of positive and negative. This is known as electric polarization. Dielectric polarization. Let's see what are the types of the dielectrics. So here, dielectrics are characterized based on the type of molecule present in the material. So here, dielectrics are classified based on the molecules present in the material. There are two types of dielectrics: polar dielectrics, non-polar dielectrics. First one is what? The first one is polar dielectrics. Second one is non-polar dielectrics. Let's see. What are the polar dielectrics? Before that one, I would like to recall what is what is molecule. Molecule is nothing but a compound which was formed by a group of atoms. More than one atom, if combined with the another atom, the group of atoms more than two atoms in a system, that will be defined as the molecule. For example, if you take the water molecule, in the water molecule, hydrogen and oxygen, two atoms will be present. If you take carbon dioxide, it will have carbon and oxygen. So the combination of two atoms or more is considered as molecule. So here, based on the molecular character, based on the molecular concept, the dielectrics are classified into polar and non-polar. Let's see what is polar dielectrics. In polar dielectrics, the center of mass of positive charge does not coincide with the center of mass of negative charge in the molecule. Hence, dipole moment exists. The molecules are irregular in shape. So, what is that? So, here just imagine a molecule. In this molecule, there are two atoms, of course, present. So, for example, for one atom, I'm taking a positive charge. For another atom, I'm taking as a negative charge. If these two charges, the center of mass of positive charge, the center of mass of negative charge, if not coinciding in a proper way, they are not coinciding exactly. So, this is non-interaction of positive charge and negative charge. So because of this non-interaction of positive and negative charge exactly will be formed dielectric. When the charges of positive and negative are not coinciding in a proper way or exactly, then there will be dipole moment is exist. Dipole moment is exist. So because of the dipole moment existence, it will be defined as polar dielectrics. In polar dielectrics, what are the shapes of the molecule? So in polar dielectric, the shape of the molecule is irregular. Means one positive side if may be large, negative side may be small. If the positive charge is small, negative charge will be high. So this is about the shapes of the polar dielectrics. That is the reason it will be defined as irregular in shape. So this is about the schematic diagram. See, positive charge and negative charges are not coinciding except these two figures. So see here, positive and negative charges are not coinciding in a proper way. So this is called as the polar dielectric figure. When the electric field is applied, the molecules align themselves with the electric field. So here, for the polar dielectrics, when polar dielectric is placed in the presence of electric field, what will be happen? When polar dielectric placed in the presence of electric field, whatever molecules are there in the polar dielectric align themselves. The molecules of the polar dielectrics align themselves. So in case there is no electric field, if you are remove the electric field, what will be happen? When the electric field is removed, a random dipole moment is observed and net dipole moment in the molecules will be zero. What will be happen? When they align themselves, it will be formed dipole moment. In the presence of electric field, it will be formed dipole moment. If electric field is removed, so here, whatever molecules are there, the molecules are aligned randomly, and moreover, because of this randomness, dipole moment is zero in the absence of the electric field. You can see the figure also. In the figure one, in this figure, they align in a proper way. That's the reason dipole moment is exist. Here, this is absence of electric field. That is the reason no dipole moment. Here, aligned properly systematically, here aligned in random, so that is the reason no dipole moment. Here dipole moment is present. Coming to the examples, what are the examples of the dielectric polar? So that is HCl H2O, H plus Cl minus H plus Cl minus H2O. So this is about the for our dielectrics example. What are the examples? I am taking only two examples, that is HCl and H2O, or the H2O are the best examples of the polar dielectrics. Coming to the non-polar dielectrics. In the non-polar dielectrics, the center of mass of positive charge and negative charge coincide in a molecule. Hence, no dipole moment is exist. These molecules are in a regular shape, means in a systematic shape. What is the definition? In a dielectrics, where the center of positive and negative charges are coinciding, where the center of positive charge and negative charge coincide in a molecule, that is called as non-polar dielectric material. So here what is that? So just take the molecule. Here is the positive charge, here is a negative charge. Both are coinciding exactly. Both are coinciding exactly. This is known as non-polar dielectric. So when the positive charge and negative charge coinciding exactly, then no dipole moment is existing. This is the reason it will be called a non-polar dielectric material. And what are the, see, this is about the schematic diagram. See, the positive and negative coinciding exactly, so no dipole moment, and hence it is non-polar dielectric. Let's see what are the examples. The examples are H2O2 N2, H2O2 N2, CO2. CO is polar dielectric, CO2 is non-polar dielectrics. So here these are the examples of the non-polar dielectric materials. Coming to the differences, polar and non-polar. Polar dielectrics are the polar compound that cannot conduct electricity. So here you know very well about what is polar. Polar dielectrics are formed by polar compounds. Coming to the non-polar. Non-polar dielectrics are formed from non-polar compounds. Even in polar and non-polar, there is no conductivity character. Coming to the shape, in polar, the shape is asymmetric. In non-polar, it is symmetric. That means it is a proper shape. In polar, no proper shape. And what are the bonds exist in polar dielectrics? In polar dielectric, the bonds are existing polar. In non-polar, non-polar bond existing. Coming to the examples, HCl. Coming to here, for the non-polar, it is benzene, methane, carbon dioxide are the good examples of the non-polar dielectrics. Next one, types of the dielectric materials. Right now you saw that one. Classification of the dielectric based on the molecules. Now, based on the materials nature, based on the medium nature, based on the state nature, dielectrics again classified into three types. Dielectric materials can be solid, liquid, or gas. Even high vacuum can also used as a dielectric. Solid dielectrics are the most commonly used materials. Example, glass, rubber, mica. And liquid dielectrics are transform oil, cable oil, capacitor oil, vegetable oil. Coming to the gas dielectric materials, here they are air, hydrogen, nitrogen, helium. So here, based on the state of the nature, dielectric material classified into three types: solid, liquid, gas. For the solids, it is just glass, rubber, mica can be considered as a solid dielectric material. For the liquid, transformer oil. For the gas state, we can take hydrogen or air. Let's see solid dielectric materials. These are the most commonly used in electrical engineering. These are very good insulators. Rather, solid dielectrics. These are the most commonly used in electrical. Solid dielectrics are used. Solid dielectrics are used in electrical engineering. They are the very good insulators. Let's see what are that. So, in that one, first one I'm discussing about the mica. This is an inorganic material made up of silicate of aluminum with silicate of soda and potassium magnesium. So it is an inorganic material. It is made up of silicate of aluminum and soda. Along with silicate of aluminum soda, it consists of potash and magnesium. It is rigid, tough, and strong. Strong material, tough material, resin material. And it has high dielectric strength and not affected by matter. What is the strength? The strength is high and not affected by the matter. It is widely used in irons, hot plates, and toasters. So here in iron box, in hard plates means in pressure cookers, this this mica is useful as an insulating material. So this is a figure of the mica which we got from Google. The figure we taken from the Google. Coming to the glasses. Glass is one of another dielectric material. This is an organic material made by the fusion of different oxides like silicon oxide, zinc oxide, magnesium oxide. What is fusion? Fusion is nothing but combination. Here, glass is an inorganic material which is formed by with the help of silicon oxide, zinc oxide, magnesium oxide. So here it is a brittle and hard material. It is a good the conductivity also the strength of the dielectric material is good, mostly used in the capacitors. It used as dielectric tubes in radios and television. Coming to this is about the glass. Even you can see the TV. So when you observe the television, in the television, the whole body is made of with the plastic and the display is made of with the glass. But when you touch the glass, you won't get any shock. The glass is shock proof because the glass is a dielectric material. So next one, asbestos. This is a natural occurring material. It consists of magnesium silicate. It has low dielectric strength. It is used as insulating material to prevent the current flow in the outer body. It is widely used in the form of paper, tape, cloth. So this is the figure of the asbestos. It is a mineral. Coming to the rubber, this is one of the examples of the solid dielectric material. This is a it is spelling mistake. This is organic material. This is organic polymer. It may be natural or synthetic. It may be prepared natural or synthetic. It has good electrical and thermal properties, and also it has a good tensile strength. It is used for the insulating material on the electrical wires. So right now the electrical cables are used with this rubber. So the copper coil, the copper wire, it is produced with the rubber, where rubber is working as a good dielectric material. So this is a simple figure for the rubber material. Coming the last one in the dielectric, that is solid dielectrics, that is ceramics. The ceramics are the non-metallic inorganic compounds such as silicates, aluminous oxides, carbides, borides. So what is considered? The ceramic is considered aluminum, silicates, oxide, carbides, and borides. Ceramics can be classified clay products, refractory products, glass products. Ceramics are hard, strong, and dense. Ceramics nature is what? Hard, strong, dense. They have excellent electrical and mechanical property. They have excellent dielectric and mechanical property. They are widely used as insulator in switches, plug holders. So how they can be useful? They can be useful as a switch as well as plug holders. They are also used as dielectric in capacitors. So this is about the ceramic capacitors are the good conductors, sorry, good dielectric. They are also known as the good dielectric materials. Coming to the liquid type of the dielectric materials. There are three types of liquid dielectrics. The first one is insulating mineral insulating oil. These oils are obtained from crude petroleum by distillation. These oils possess high oxidation resistance and have good thermal stability. These oils are used in transformers and capacitors. So here, mineral insulating oils are the liquid dielectric materials, and these materials having high oxidation resistance and good thermal stability, and these oils can be used in transformers and capacitors, And the examples of this mineral insulating oil are transformer oil, cable oil, capacitor oil. So this is a figure which I took from the Google. So about the second one, synthetic insulating oil. These oils are very much resistant to oxidation and fire hazards. They are used as coolant and insulators in high voltage transformers. So here synthetic oils are nothing but prepared oils. These are the good resistant to oxidation and fire hazards. They are used in transformers, and the examples of synthetic insulating oil is Aerocolors, Savol, Ascaryls and Sovatel. This we took from the, again this is source of the figure where I took this. So this is Eden oil UK source. And the third one is a miscellaneous insulating oil. The dielectrics of these oils is the same as that of mineral oils. These oils are used in high voltage transformers, example vaseline, vegetables and silicon. Third one is what? Miscellaneous insulating oil. This is also another dielectric material in liquid type, and this is the figure about the vegetable oil which I took from the Google. And coming to the third type of the dielectric material, or the gaseous dielectric materials, the first one is air. Air is naturally available dielectric material. It is the most important insulating material. The dielectric loss is practically zero. The dielectric constant increases linear with the increasing pressure. When pressure is increasing, dielectric constant also is increasing. It is used as dielectric in condenser. It can be used as insulation only in low voltage application. So this is air about the air, which is the gaseous dielectric material. Coming to nitrogen, it is an important gaseous dielectric. It is chemically inert gas. It prevents oxidation and reduces the rate of deterioration. In oil filled transformer, it is used to replace oxidizing atmosphere. It is also used in capacitor and cables under pressure. So this is about the nitrogen dielectric material, which is a gaseous state example. Sulfur hexafluoride. It is formed by burning of sulfur in the fluorine atmosphere. It has superior cooling properties than that air and nitrogen. It is better than nitrogen and air. It has high chemical stability up to 1000 centigrade. It is used in transformers, electrical switches, Van der Graaf generators, voltage stabilizers, and X-ray apparatus. So this is about the sulfur hexafluoride. So here, air, nitrogen, sulfur hexafluoride are the gaseous type of dielectric materials. Coming to the applications of dielectric materials. The dielectric material based on the nature of state, they have variety of applications in electric engineering field. Major applications in capacitors and transformers. So they are majorly applicable in transformers and capacitors. Dielectric materials in capacitor is store electrical energy. Dielectric materials and capacitor is to store electrical energy. Based on the nature of dielectric material used, the capacitor fall into various groups. So by using of method, by using of nature of material, the capacitors are classified into four types. This, let's see. Capacitor with vacuum air glass. Okay. This also we took from the Google, this figures. So capacitors, they are used in radio frequency and low frequency circuits. They are used in radio frequency and low frequency circuits. Capacitor with the only solid. They are used in laboratory as standard capacitors. Capacitor with minerals. They are used in high voltage application where large value of capacitance is required. Capacitors with combination of solid and liquid. They are used where precision is not important but a high value capacitance is required. Applications of dielectric. So what are the four groups? So that is, the first one is capacitor with vacuum and air gases. are applicable in radio frequency, low frequency sector. Capacitor with the only solid used in laboratory as solid standard capacitor. Capacitor with the mineral oil, they are used in high voltage application. Capacitor with the combination of solid liquid used in capacitance. Coming to the transformer, applications of dielectric in transformer. The major role of dielectric in a transformer is to insulator as well as cooling agent. So it will be as an insulator as well as cooling agent in transformer. Transformer divided into with the gas dielectric material with the liquid dielectric materials. So based on the usage again, the dielectrics in the transformers again it will be considered as gaseous dielectric, liquid dielectric. Coming to the another topic, this is about the properties of good dielectric material. So what are the properties of good dielectric material or ideal dielectric material? It should have high resistance to reduce leakage current. It should have high resistance to reduce the leakage current. It should have high dielectric strength. It should have high dielectric strength. It should have high mechanical strength. It should have high fire resistance. It should have low thermal expansion. It should have high thermal conductivity. It should have a low dielectric loss. It should have low water absorption quality. So, what the characteristics of good dielectric material? Should have high resistivity to reduce leakage current, should have high dielectric strength, should have high mechanical strength, should have high fire resistance, should have low thermal expansion, should have high thermal conductivity, should have low dielectric loss, should have low water absorption quality. So these are the characteristics of good dielectric material. Coming to the properties of dielectric. Some of the properties of dielectric materials are dipole moment, dielectric susceptibility, dielectric polarization, dielectric displacement, dielectric constant. Let's see what is dipole. A dipole is an entity in which equal positive and negative charges are separated by a small distance. You discussed previously about the dielectric polarization where the positive and negative charges are separated in the presence of the electric field. So the separation between positive and negative charge is defined as a dipole. Two poles. That means what? Two poles. That means positive charge and negative charge are separated with certain specific distance. That is called as dipole. Let's see dipole moment. The product of magnitude of either of the charge and separation distance between them is called dipole moment. So here that means what? Q into x. What is q? Q is nothing but charge. X is what? Distance. So the product of magnitude of either of the charges and separation distance between them is called dipole moment. You can see figure where mu e dielectric moment is what? Q into x. All dielectrics are electrical insulators and they are mainly used to store electrical energy. So this is about the dipole. See, the positive and negative charge both are separated in the presence of electric field. So this is considered as a dipole moment. So dipole. Dielectric constant. What is dielectric? Dielectric constant is the ratio between permittivity of the medium to the permittivity of the space. So here what is that? It is a ratio, simply it is a ratio between E by epsilon by epsilon naught. What is epsilon? Permittivity in medium. What is epsilon naught? Permittivity of vacuum. But the ratio between permittivity in medium to permittivity of vacuum is defined as dielectric constant and it is represented by epsilon r. For vacuum, the permittivity is 1. For the other dielectric material, the dielectric constant is more than 1. So here, the characteristics of dielectric material are determined based on the dielectric constant. It has no units. It is a dimensionless factor, and moreover, the character of dielectric material is determined on the basis of dielectric constant. Dielectric permittivity. It is a property. What is dielectric permittivity? It is a property which characterizes the degree of electrical polarization of a material experience. There is a spelling mistake. Of a material experiences under the influence of the external electric field. It is a property which characterizes the degree of electrical polarization of a material experience under the influence of external electric field. How the material is characterized, how the material is influenced in the presence of electric field is defined on the basis of the permittivity. Permittivity in vacuum medium epsilon. How much electric field generated per unit charge in the medium? What is permittivity in medium? How much electric field generated per unit charge in that medium? Epsilon naught. The electric field generated in vacuum, it is constant. What is the value? 8.85 into 10 to the power of minus 12 farad per meter. Electric field. The region surrounded by charged body is always under the stress because of electrostatic charge. If the small charge Q or a charged body is placed in this region, then the charge Q or a charged body will be experience a force according to the Coulomb law. The stressed region around the charged body is called electric field. What is that? The stressed region around the charged body in the electric field, the stressed region around the charged body is called electric field. What is that? Electric field, nothing but the field created by electric forces, is called as the electric field, which is as per the Coulomb law. We have another definition. The region surrounded by the charged body is always under the stress because of electrostatic charge. If a small charge Q or a charged body is placed in this region, then the charge Q or charged body will be experience a force according to Coulomb law. The stressed region around this charged body is called electric field. So as of the Coulomb, a force is created a particular field, electric force is created a particular field, that field is defined as the electric field. Electric field at any point defined as the force that acts on a unit positive charge placed at the point. So what is exactly electric field at the point? Defined as the force that acts on a unit positive charge placed at the point E. At the point. It is denoted by symbol E. Polarizability. The induced dipole moment per unit field is called polarizability. The induced dipole moment per unit electric field is called polarizability. The induced dipole moment per unit electric field is called polarizability. We know that the induced dipole moment is proportional to the intensity of electric field. The induced dipole moment is proportional to the intensity of electric field, so that mu is proportional to E. Therefore, mu is equal to alpha E. When you remove the proportionality, it will be alpha E, where alpha is the polarizability constant. Polarization vector. Definition. Induced dipole moment per unit volume of dielectric medium. Induced dipole moment per unit volume of dielectric medium. Briefly, P is a vector quantity and its direction is along the direction of applied field. If M is the average induced dipole moment per unit molecule, N is the number of molecules per unit volume, then the polarization is given as P equal to N nu. We have another definition, the product of N and mu, where N is the number of molecules, mu is the dipole moment. So the product of n and mu is defined as the polarization vector. We have another definition. Inducible moment per unit volume of dielectric medium is defined as the polarization vector. Electric flux density. Electric flux density is defined as the charge per unit area, and it has same units of dielectric polarization. Electric flux density is defined as charge per unit area. Electric flux density is defined with the symbol D at the point in a free space or in a term of the electric field strength is what? D is epsilon naught, and E I am taking as equation 1. At the another point it will be considered as what? D equal to epsilon and E. From the equation 1 equation 2 it will become, as the polarization measures the additional flux density arising from the presence of material as compared to the free space. So from this concept we simply define as D equal to epsilon naught E plus P. So this is from equation 3 and 2 I can consider epsilon E is equal to epsilon naught E plus P. So from this equation epsilon naught, sorry, E is a common, so epsilon minus epsilon naught of E equal to P, or what is epsilon? Epsilon you can write from the dielectric constant definition, that can become epsilon r equal to E by E naught, sorry, epsilon by epsilon naught. So from that concept we can write epsilon r into epsilon naught minus, what is epsilon r? Epsilon r nothing but epsilon by epsilon naught. From this concept it can be considered as epsilon r into epsilon naught minus epsilon naught into E equal to P, where again it can be considered epsilon naught is a common, so you can simply define as what? That is epsilon r minus 1 into epsilon naught into E equal to P. This is the relation between electric field, polarization vector, and dielectric constant. Dielectric susceptibility. The polarization vector P is proportional to the electric flux density and direction of the electric field. Therefore, polarization vector can be considered as P equal to epsilon naught susceptibility of electricity and electric field E. Therefore, susceptibility of electric is what? P by epsilon naught and E. So what is dielectric susceptibility? That is a ratio between P by epsilon naught into E. So from the previous definition, P equal is what? P equal to epsilon naught into epsilon r minus 1 into E by epsilon naught into E. So for the simplification, epsilon naught and epsilon naught will be cancelled. Then finally what E and E will be cancelled, and finally susceptibility E is what? Epsilon r minus 1. Polarization in dielectrics. What is the polarization is dielectric? The process of producing the process of producing electric dipoles in the presence of direct current or DC electric field is called polarization in dielectric. The process of producing electric dipoles, sorry, it is spelling mistake, dipoles, dipoles. The process of producing electric dipoles in the presence of the DC electric field is called as polarization in dielectrics. There are various polarization we have based on the various method. There are various polarization, and they are electronic polarization, ionic polarization, orientation polarization, space charge polarization. Let's see what are that. Electronic polarization. When an electric field is applied to an atom, when an electric field is applied to an atom, positively charged nucleus displaces in the direction of the field, and electric cloud inside the negative electrons in opposite direction. Positive charges are moves in the same direction of the applied electric field, and negative charges moves in the opposite direction to the applied field. This kind of displacement will produce electric dipole within the atom. That means dipole moment is proportional to the magnitude of the field strength, and it is given as mu is proportional to E, or mu E equal to alpha E into E, where alpha E is called as electronic polarizability constant. When an electric field is applied to an atom, positively charged nucleus in the direction, so this is again, sorry, it is repeated. So this is about the electron. Alpha is electronic polarizability constant. Mu is the electric field. Sorry, E is the electric field. Mu E is mu E is dipole moment of electronic expression. What is the equation for? Consider an atom in electric field. In an electric field, intensity is E. Since the nucleus positive is what? Nucleus here I am taking as ZE, and electron cloud is what? Negative electron cloud is minus ZE, positive electron cloud is plus ZE. Of the atom have opposite charges and acted by the Lorentz force Fl. Subsequently, nucleus moves in the direction of the field and electrons in opposite direction. When electron cloud and nucleus get shifted from their normal position, an attractive force between the is created and the separation continues until Coulombic force is balanced with the Lorentz force. Finally, a new equilibrium state is arised. Let's see, this is about the figure in the absence of the field, in the presence of the field. So plus ZD is a nucleus, so R is the radius. So from figure 1, figure 2, so figure 1 is about the in the absence of field, figure 2 is the presence of the field. From the figure 2, we assume that the negative charge in the cloud uniformly distributed over the sphere radius r. From the figure 2, we assume that the negative charge in the cloud uniformly distributed over the sphere radius r. Let sigma be the charge density of the sphere. It considered as sigma equal to minus ZE by 4 by 3 pi r cube, where minus ZE represents total charge in the sphere. Negative charge in the sphere of radius x is what? That is sigma into 4 by 3 into pi. So where r is replaced by x, so 4 by 3 into pi x cube, where sigma is what? Sigma is considered as sigma is minus ZE by 4 by 3 pi r cube. Replace here, then simplify, then what you will get, that is, see, pi will be cancelled, for pi by 3, for pi by 3 will be cancelled, then this one will be cancelled, and pi will be cancelled. Finally minus ZE by r cube into x cube. This considered as equation 1. But from the Coulombic force, what is that? 1 by 4 pi epsilon naught into q1 q2, that means qp by r square, where r is replaced by x square. So replace here. So what is qe? Qe is, what is qe? We took that one. Qe is what? Minus ZE by r cube into x cube. Replace here. So again what will be happen? So here, so x square x cube, so 1x will be here, then remaining thing is minus z square e square x by 4 pi epsilon naught into r cube. Force experienced by displaced, that is we take an equation to force experienced by the displaced nucleus in electric field of strength E is considered as Lorentz. So here what is Lorentz force? Fl equal to Eq, where Eq is considered as ZEE. So this is equation 3. ZE means what here? ZE is nothing but cloud of electron, is electric field. So for the equilibrium status, it will be considered as Fl equal to force of Lorentz equal to force of Coulombic. So from the equation 3 and 2 and Lorentz concept, we can consider z minus z square a square x by 4 pi epsilon r cube equal to ZE. So here what is happening here? So here E will be cancelled out, and finally you are getting that one. what is happening? E will be cancelled, and finally minus ZEX by alpha you are getting, where E is considered as what? E is considered as dipole moment by electronic polarizability. So this is about the electronic polarizability evaluation part. So alpha is what? Alpha is considered as 4 pi epsilon naught into r cube. This is about the electronic polarizability. Hence, electronic polarizability is directly proportional to the cube of radius of atom. Cube of radius of atom. Cube of radius of atom. Electronic polarizability characteristics. It encourages the increase of volume of atom. This kind of polarization mostly exhibited in monatomic gases. It occurs only at the optical frequency, that is 10 to the power of 10 to the power of 15 Hz. It is independent of temperature. Coming to the B, ionic polarization. This ionic polarization occurs when atoms form molecules, and it is mainly due to the relative displacement of the atomic compounds of the molecules in the presence of the electric field. The ionic polarization occurs when atoms form molecules, and it is mainly due to the relative displacement of the atomic components of the molecule in the presence of an electric field. When electric field is applied to the molecule, the positive ion displaced by x1 to the negative side of the electric field, and negative ions displaced by x2 to the positive side of the field. So this is displacement character, and expression is what? The resultant dipole moment mu is considered as q of x1 plus x2. So this is about the figure of the ionic polarization. And for the electronic polarization, you can take the dielectric polarization concept figure. So x1 cation, x2 is the anion. So anion cation will be displaced because of displacement. Because of their displacement, ionic polarization is existing. Restoring force constant depends upon the mass of the ion and the natural frequency. It considered as F equal to AE, where F equal to m omega naught square into x, or x equal to EE by m omega naught square, omega naught square, where x1 plus x2 is what? So that is EE by omega naught square of 1 by m1, sorry, 1 by m plus 1 by capital M. So here mu of ionic is what? E of x1 plus x2, and where it will be considered as what is x1 x2? X1 EE by omega naught square of 1 by m plus 1 by m. You replace the values, then finally simplify alpha. This in later slide I can explain this evaluation once again, but due to the time I am moving very quickly. In next video I will put this evaluation and equation parts in another video also. So alpha ionic is considered mu ionic by E, that is a square by omega naught square of 1 by m plus 1 by m, where small capital M is about the anion, small m is about the cation of the mass. Ionic polarization characteristic. This polarization occurs at the frequency 10 to the power 13 Hz. In the IR radiation, it is a slower process than the electron polarization. It is independent of the temperature. Polarization orientation, this is orientation polarization. Orientation polarization, it is also called as a dipolar or molecular polarization. The examples are N2 H2 O2 Cl2. Doesn't carry any dipole because of the center of the positive charge, center of the negative charge coincided, and the molecules like methyl chloride, water, HCl carries dipole even in the absence of electric field. However, the net dipole moment is negligibly small since all the molecular dipoles are oriented randomly when there is no EF. In the presence of the electric field, these all dipoles orient themselves in the direction of the field. As a result of the net pole moment becomes high. Expression is what? Expression is P equal polarization vector concept. N P equal to N mu, where N is what is mu? Mu is nothing but dipole moment. So N mu square E by 3 kt N alpha naught E, and alpha naught is what? Mu naught mu orange square by 3kt. Orange is polarization character. It occurs frequently 10 to the power 6 to 10 to the power 10x. A slow process compared to the ionic polarization. It greatly depends on temperature. Langevin-Debye equation. The total polarizations of electronic ionic orientation is considered as the Debye-Langevin equation, and it is about 4 pi epsilon naught r cube for the electronic polarizability. For the ionic polarizability is squared by omega naught square of 1 by m plus 1 by m of anion cation, and orientation mu naught square by 3kt. So these combination of electronic, ionic and orientation polarizabilities or summation is called as Langevin-Debye equation. Internal field or local field. Local field or internal field in a dielectric is the space and time average of the electric field intensity acting on a particular molecule in the dielectric material. Evolution of electric field. Consider a dielectric placed between the plates of the parallel plate capacitor, and let there be a imaginary spherical cavity around the atom A inside the dielectric. The internal field at the atom site A can be evaluated with the four components of the field E1, E2, E3, E4. So this is the figure about the internal field. So we have the above the positive charge, below the negative charges. Between this one a spherical cavity of atom is present. So here what will be happen at the field E1. E1 is the electric field intensity at A due to the charge density on the plates. E1 is considered as d by epsilon naught, where d is considered as epsilon naught into E plus P. So A1 is considered as epsilon naught E plus P by epsilon naught. Therefore, E is considered as A1 is considered as epsilon naught will be out here. So epsilon A1 equal to epsilon. Sorry, A1 equal to E plus P by epsilon naught. This is considered as the equation 1. Coming to the field 2. E2 is the field intensity at A due to the charge density induced on the two sides of the dielectric due to the polarization. So it will be considered as the E2 equal to minus P by epsilon naught is considered equation 2. At E3. E3 is the field due to the dipoles within the cavity, which depends on the crystal structure. Here we have considered the cubic structure. So E3 is 0. Equation 2 is minus P by epsilon naught. Equation 3 is E3 equal to 0. From this figure, it will be analyzed that this is due to the polarization charges on the surface of the spherical cavity. Therefore, dA is considered as 2 pi PQ QR. dA is considered as 2 pi. PQ is considered again what? R sin theta. QR is considered as what? R d theta. So finally it will be considered as 2 pi R square sin theta d theta, where dA is the surface area between theta and theta plus d theta. The total charge present on the surface area dA is considered as dq. It is considered as normal component polarization and surface area. Therefore, dq equal to p cos theta into dA, where p cos theta is considered as what? Into dA is considered as 2 pi r square p cos theta into sin theta d theta. The field due to this charge at the A denoted by, after simplification, it will be considered as 1 by 4 pi epsilon naught dq by r square. Theta is 0, therefore 1 by 4 pi epsilon naught dq cos theta by r square, and further it will be simplified as dE4 is considered as 1 by 4 pi epsilon naught r square 2 pi r square p cos theta sin theta d theta into cos theta, and finally it will be considered as dE4 is 1 by 4 pi epsilon naught dq by r square. So this is only again repeated. So here I can consider dE4 is considered as 1 by 4 pi epsilon naught dq by r square. Hence the total field E4 due to the charges on the surface of the entire cavity is considered as integration from 0 to pi, that is dE4. So p by 2 pi epsilon naught cos square theta sin theta d theta, p by 2 epsilon naught 0 to pi cos square theta sin theta d theta. Let x is the cos theta, dx is sin theta d theta. P by 2 epsilon naught integration from 0 to minus 1 x square dx minus p by 2 epsilon naught x cube by x minus to the power of minus 1 minus p by, after further simplification, minus p by 2 epsilon naught of minus 2 by 3, then simplification, that will be p by 3 epsilon naught. So from the field E1, E2, E3, the internal field considered as, from E1 it is A plus P by epsilon naught, from E2 minus P by epsilon naught, from E3 it is 0, from E4 P by 3 epsilon naught. Then it will be what? A internal field or local field is considered as A plus P by 3 epsilon naught. Classes Moshe's relation. Another topic. Consider a dielectric material having cubic structure and assume the ionic polarizability or antipolarizability are 0. Alpha I, alpha O are the 0. Polarization vector P or polarization P is considered n mu, where n is considered, P is again considered as P equal to n alpha E alpha E into EI, where mu is the alpha alpha E and EI, where EI is what? EI is considered again E plus, from the internal field, E plus P by 3 epsilon naught. Therefore P equal to n alpha E EI, n alpha E. So replace the value of EI, that is E plus P by 3 epsilon naught. So n alpha E plus n alpha E P by 3 epsilon naught. Then simplification, n alpha E equal to P minus n alpha E P by 3 epsilon naught. Taking the common, P of 1 minus n alpha E by 3 epsilon naught equal to n alpha E. P equal to n alpha E by 1 minus n alpha E by 3 epsilon naught. This is an equation 1. We know that the polarization vector P equal to epsilon naught epsilon r minus 1. This I can take as equation 2 from equation 1 and 2. N alpha E by 1 minus n alpha E by 3 epsilon naught equal to epsilon naught E into epsilon r minus 1. For the simplification, 1 minus n alpha E by 3 epsilon naught, which equal to n alpha E by epsilon naught into E into epsilon r minus 1. Again for the simplification, 1 equal to n alpha E by 3 epsilon naught plus n alpha E by epsilon naught into E into epsilon r minus 1. 1 equal to n alpha E by 3 epsilon naught plus n alpha E by epsilon naught of epsilon r minus 1. 1 equal to n alpha E by 3 epsilon naught of 1 plus 3 by epsilon r minus 1. Therefore n alpha E by 3 epsilon naught equal to 1 by 1 plus 3 by epsilon r minus 1. Further, n alpha E by 3 epsilon naught equal to epsilon r minus 1 by epsilon r plus 2. This is about the CM relation, classes Moshe's relation. And finally, classical theory of electronic polarizability. Classical picture of an atom is that there is heavy, immobile, unformable, undifferable nucleus surrounded by electronic cell of JDA charge connected to the nucleus by harmonic spring type F equal to minus kx. If x is the displacement of electronic under the effect of local electric field, then we get minus E local equal to kx, where it is equal to m omega naught x square, which we taken as 1, where k is a four constant between the positive heavy molecule and the electron cloud. Omega naught is the natural frequency of oscillation of atoms, pictorially shown in the figure 1. So sorry, this figure I forgot to insert here. We want to develop, next video I will put this one. We want to develop a simple model that describes the frequency of dependence of a electronic polarizability. Let omega frequency of electric field. The field at any time is given by E local sine omega t. The equation of motion is given by m d square x by dt square plus m omega naught x square equal to minus E local sine omega t, which we taken as equation 2. In addition, under the influence of the varying electric field types in given by x equal to x naught sine omega t. Putting equation 3 in the equation 2, we obtain minus m minus omega square plus omega naught square into x naught, which is equal to minus e into E local, which we taken as equation 4. The amplitude of corresponding dipole moment is given by P equal to minus E x naught, which we taken as equation 5. Therefore P equal to E square E local by m of omega naught square minus omega, which we taken as equation 6. Now the electronic polarizability is given by E electronic polarizability by F P orientation by E local, which will be second taken as equation 7. We get alpha electronic equal to E square by m omega naught square minus omega, which we taken as equation 8. This type of frequency depends on electronic polarizability. So in the equation 8, there are cases arises omega is very less than to the omega naught. Therefore alpha electronic is equal to E square by m omega square, which we taken as equation 9. The equation 9 is about the static or independent of frequency of electric field. So this is equation 8, that is alpha electronic is a classical theory of electronic polarizability. Alpha electronic is considered as A square by m by omega naught square minus omega square. So equation 8 is your answer. So this is about the electronic classical theory of electronic polarizability. So internal field is the important, so internal field and various polarization and classes motion equation. This again I put the another video for the valuation part of the various polarization, classical motion equation and other related important topics. Again I will put the in separate video for you. Keep watching. Thank you.